So here is the workflow used for the impeller optimization, where the blade loading and meridional geometry parameters are used to generate the blade shape in Turbo Design 1, and then the resulting performance parameters are fed into Turbo Design Optima, which basically applies MOGA to drive the solution towards the optimum design. And of course, we start by selecting the range of parameters for the inputs, which are the blade loading parameters and also the meridional geometry parameters, because it also has an influence on the blade to blade passage size and therefore the solid handling characteristics of the impeller. And then these are the constraints that are used. So the geometric constraints are selected to avoid high back sweep angle at the trailing edge and high bowing at the leading edge, whereas the secondary flow and profile loss are constrained to avoid high losses at the design point. The overall diffusion ratio is limited to avoid large separation at lower flow rates, and then the minimum surface pressure is constrained for cavitation performance. And finally, for the optimization objectives, the leading edge lean angle is minimized to avoid high blade stresses, and also the minimum channel distances in 3D as well as the 2D orthogonal projection are maximized to expand the narrow sections in the passage. So once the optimization completes, which is very fast and only takes about half an hour or so on a single core machine, we can see all the designs on a scatter plot between any two objectives. In this case, the minimum channel distance in 3D on the x-axis and the one in 2D on the y-axis, like this. And here we have chosen to see only the feasible designs which respect all of our specified constraints, and the target case, which is the baseline impeller, actually sits here. And then we can choose to see the Pareto front of optimum designs, from which we can pick and analyze any design of interest. And in this case, we select a design which gives us a good trade-off between the minimum channel distances in 3D and 2D, while still reporting a major reduction in leading edge lean. And so we use this design for further analysis and for comparison with the baseline impeller. And in fact, this is what has changed as a result of the optimization. So compared to the baseline impeller, the optimizer recommends less afterloading and some positive leading edge incidence at the hub and midspan, along with some changes to the meridional shape as well. And as a result, the optimized impeller is clearly looking very different from the baseline. And the increase in minimum channel distance is easily seen. And also, if we look at the relative velocity distribution in TD1, then it looks much smoother, especially on the shroud suction side. Now, looking further into more results, it's interesting to see the effect on Turbo Design 1 parameters, where the minimum channel distance is significantly bigger, and the leading edge lean and bow are reduced to almost half. And when we run CFD on the optimized impeller, what we find is that even though the peak efficiency is slightly reduced, the rating point efficiency is actually higher than the baseline pump. And also the optimized impeller is able to generate a similar amount of head as the baseline. And next, the 3-inch sphere test is repeated on the optimized design, and this time it's found to be able to pass through the impeller passage quite easily, both near the leading edge and the trailing edge regions. And this confirms that the new impeller does not present any risk of clogging, and has achieved the desired waste handling levels.